Thank you, Jane. This is Mike Berg from Panduit, and I'm going to kick us off here. And so the first area I'm going to go into, and I'm going to talk more so about the structured cabling side of things here, and the physical layer, and the cabling infrastructure. So why do we need to worry about the network physical layer? And I have a green stop sign there for a reason. We tend to see that green light on the network equipment, and in our minds we think, yep, the connectivity is good. We've got our performance there based on that green light. And kind of part of our message here today is, stop when you see that green light and verify that connection. Verify that even though it says Cat 5e or Cat 6a on the cabling that you're using, are you really getting that performance? And really, what we can relate this to of what's going on in the market today, more than 50% of the failures on the plant floor actually in the network actually trace back to that data link and physical layer. So that's more than half of them. And the potential downtime associated affects the OEE, and it can be costly for the end user. And the best in class manufacturers in terms of OEE, those who have a 90% plus in OEE, actually spend more time on the data link reliability and the physical layer. So a really important point to kick us off here. And also recognize when we don't baseline the original cable installation, we don't really know its capability, and it makes it difficult to grow that network when upgrades need to occur or when migrations need to occur. And we need to recognize as well that that cabling plant is going to be in there a lot longer than the hardware that's connected to it. In most cases, the switches, the electronics are going to switch out 4 times over the life of the cabling that's put in. So we need to think about that as we're installing these systems. And then the relevance here as well is that we all see this happening every day, that the number of network devices is increasing, and of the plant nodes, more than 50% of them are now on some variant of Ethernet. So a disciplined approach to the network can help us reduce risks and improve processes. So what Jim and I are here to talk to you today, and today's topic, it's kind of 2 topics really. It's the network planning side of things, which I'm going to cover, giving you some guidance on installing the cabling infrastructure for reliability and availability, and making that standards based. And then the second part is going to be how you can better plan that system for baseline testing to improve your knowledge of the system and performance, and your ability to troubleshoot, which can lead to reduced costs for both the SI and the end user. So I'm going to be referring to standards, IT standards, from an organization called TIA. TIA is a Telecommunications Industry Association. TIA is recognized across many different building applications or premises by IT organizations in North America, and it is the standard for network design and deployments. If you're sitting in a commercial building today, your network is distributed following the TIA commercial standard. And accordingly, different premises, data centers, healthcare facilities, and industrial plants also have premises standards associated with TIA. So you may be somewhat familiar with some of the things that come out of the TIA standard. So if you're familiar with the 328-foot copper limitation, it's a part of the common standard, the 568C that you see on the left. And the connectors that are used out in the industrial premises and in commercial buildings, those are also recognized through the TIA standard. So whether it's an RJ45 or an M12 and the Cat 5e versus a Cat 6 or a Cat 6a performance, and then also fiber optics as well. So this is the TIA standard, and it's what I'm referring to as we go through the presentation today. And the particular standard that covers the industrial premises that we have highlighted there is TIA 1005A. So part of TIA is this TIA 1005A model, and this is a basic architecture that defines the structure of the cabling and connectivity that go into the industrial premises. So as we look at this diagram, there's a lot of different indicators here, so I'll kind of go through those. It starts at the bottom where EO stands for the equipment outlet. And then there are 2 and sometimes 3 sets of patching systems or distributors, which are the D boxes, on the way up to the network core, which is at the top. From the bottom up, these are depicted as distributor A, distributor B, and distributor C. And you may be most familiar with distributor C and the patching that will be the patch panels and patching that would be co-located with the actual network core equipment in a telecom room, for example. The cabling subsystems also start at the bottom and move towards the network core. So this is actually defining the structured cabling. So the links that connect the equipment outlet is cabling subsystem 1, and then moving up you have subsystem 2 and subsystem 3 attaching the network core. So at each distributor level, there is a cabling plant or a channel defined. Within the distributors are where the patching interconnects or cross connects occur, providing a testable and scalable plant floor cabling infrastructure. You'll also notice that this model is quite flexible, so it allows for variations in what the network topology being used is. So there's a lot of variation to adapt to the logical design. And so I put this overlay of a typical plant floor diagram to kind of give you a feel for where TIA 1005A and the industrial premises typically sits in the industrial network topology. So within the plant floor networks, the structured cabling environment lives in conjunction with the connectivity system for the industrial computing platform at level 3 in the purple there. And then intermediate distribution frames, or the ways that we distribute the switches out on the plant floor, are at level 2. And then the more industrial switches at the access layer, those switches deployed in control panels or within network zone enclosures, are at level 2, 1, or 0. So just to kind of give you a basis for how this correlates with the industrial network. So what sets TIA 1005A apart from the commercial standard? The main thing is what's at the very bottom there, and that's recognizing the dynamics of the plant floor environment. And really the adoption of this M.I.C.E criteria when evaluating that plant floor. And M.I.C.E is an acronym. It stands for things that are commonly looked for by an engineer or by a design engineer out on the plant floor. It covers mechanical, it covers ingress, it covers climate and chemical, and then it covers electromagnetic. So this is a big difference, a big part of this standard that's different than the commercial standard, which is much more of a static environment. So recognizing that difference in the architecture, we also have different things that are recognized in the standard that accommodate the difference in the nature of the deployment, such as deploying systems in control panels and then also adjusting for those M.I.C.E criteria. So with the TIA 1005A standard, you have M12 connectors that are recognized in both the D code and the X code formats. You also have 6 connector channels that are possible and recognized under TIA 1005A. This is possible to happen when you're running in and out of control panels where you need to seal that connection that's made. So you may end up with more connectors following this strategy. And then finally, the use of couplers and adapters is recognized in 1005A. So just briefly here, also recognizing in addition to TIA 1005A and the TIA standards, there are obviously industrial Ethernet technology organizations and standards that are out there, listing some of those here for you. And these organizations will typically define industrial communication networks, including the real-time Ethernet requirements, and then also related network components. So these are some of those key standards listed here, and they should always be considered along with the TIA physical layer standards, and in a lot of cases they are actually harmonized together as well. But just pointing those out for you as well, so that you're aware of them. So Panduit, what we do in terms of TIA 1005A, we try to build out our industrial network offerings around the 1005A standard and try to provide guidance around it. We call this turning the standards into solutions. What the product offerings we have that you see there across the top, there are different what we call building block solutions. And each one of those are meant to align with those distributors that I talked about earlier. And it's really around enabling that switch deployment and network device deployment at each level of the network. And what we're trying to do is try to provide that structured cabling environment wrapped around that switch deployment. So providing you the way to test the cabling plant and also the good way to deploy the switch as well. So that's each one of those devices. We can do that from that control panel level all the way up to that core network switch. And we also take into consideration the M.I.C.E. factors in the cabling as well as the enclosures that are being specified at each level. So if you see along the left there, you may be using more of an office grade fiber connection at the top levels of the network for connectivity. And you may also be using standard office grade connectivity, even in some areas on the plant floor. But as we get closer to that end user outlet and the field device level, we're more likely to require a more sealed connector, a more environment resistant connector like an M12 or some other IP67 type device. So we offer that type of solution as well. So Panduit considers that M.I.C.E. environment in both the product selection as well as the design of the system as well. So in terms of planning for the end user environment, these M.I.C.E. factors are also very critical to know where those hot spots are on the plant floor, try to avoid them as much as possible in how the network is being deployed for a better design and a more reliable design, and also to kind of control costs as well so that we can use as much office grade product as possible and also avoid those M.I.C.E. areas. So M.I.C.E. is a planning tool for the design as well. So some of the benefits in choosing M.I.C.E. rated components, providing you data around the M.I.C.E. levels or the suitability of products to the M.I.C.E. levels allows you to assess that product and its severity with the M.I.C.E. elements. And also recognizing that the environment may be variable, and it allows you to consider the worst case use as you're doing your design. We can use the M.I.C.E. concept along with the structured cabling approach, as I was saying earlier, to kind of control the costs and also do a better job of planning the system. So to give you a couple examples of how M.I.C.E. can be implemented, one way is with hardening and the hardening of equipment and how we route the cabling. So an easy way to understand that is in terms of the pathways that are used. So in a M.I.C.E. level 1 environment, where it's more of an office type environment, we may be using things like hangers and trays. As the environment gets harsher, if we're looking just at mechanical and ingress, we may go to conduit. And if we need a more sealed environment, we may be going to lay-in housing or a sealed wireway. So it kind of shows you how you can use different levels of hardening to affect the M.I.C.E. Elements, and then still use that same cabling but also address the M.I.C.E factors. So as we look at the different solutions, we can match up the products that we're using to the M.I.C.E environment and to the different subsystem levels that we're specifying for. So maybe at those higher levels of the network, we can use a typical standard grade, enterprise grade patch cord and the standard enterprise grade equipment cabinet. But then when we actually get onto the plant floor and we get closer to where the action is happening, we can have that same type of performance, but now we have a sealed IP67 patch cord that can withstand the elements, that's more robust and reliable. And we can do the same thing for that cabinet as well. Put that in a NEMA enclosure that can be environmentally controlled and it can exist on the plant floor reliably. So Panduit provides a M.I.C.E guide. So all the solutions I was showing, you can actually look them up in this guide and determine an overall M.I.C.E level, which is kind of where the arrow's pointing. And then we also give you more detailed information on the M.I.C.E criteria and the suitability of each product. So this is kind of a handy guide to have. It's important to recognize that M.I.C.E is an environment rating, and you're going to have the responsibility to assess these products and really determine their use in the environment. So we're providing this guide kind of as an aid. So looking at another part of M.I.C.E, which is the E factor or EMI. This is probably the most consequential area, maybe the most important area in terms of M.I.C.E. Problems in this area can cause intermittent performance in the network, which is one of the most hardest things to trace and to correct. So things to consider around shielding and noise. First thing is the source of the noise, determining where that noise is coming from. Is it within the cable? Is it outside the cable? How is it being brought to the control panel, for example? And then the design of the grounding and bonding system. So how are we going to handle that noise and the noise mitigation strategy? We have to understand both of those things before we really can get on to product selection. So the M.I.C.E guide will help us, but we also have to consider that source of noise and the grounding and bonding system. What we always recommend in evaluating the cable is to first look at that electrical balance of the cable, whether it is shielded or unshielded. So including the UTP cable that you're evaluating, look at that electrical balance. And the balance is really the dimensional and electrical symmetry between each pair. So as an example, the Cat6A cable standard actually requires this symmetrical design, dimensionally and electrically. So as a result, using Cat6A cable, you know it has a better balance and EMI noise immunity than previous cable types. And we're seeing a lot more Cat6A cable being used on plant floors. Once you get beyond that cable balance, consider then the types of shielding, additional shielding that you may need. And this is against those noise sources that you would have identified. So in the diagram, we're showing you some different versions of shielding that are out there. There's FUTP, SUTP, SFUTP, SFTP. And there's a slash in there in each one of those. The S before the slash indicates the shielding around the cable itself, where you're concerned about noise external to the cable. And then the S or the F after refers to the individual pairs. So you may be concerned about noise internal to the cable between pairs, or you might be worried about both of those factors. So cable selection relates to that noise source and then also to your grounding and bonding strategy. So there are also braided versions of these shielded cables. The braid relates to increasing that surface area on the shield and providing a low resistance path to drain out high frequency noise. The additional layers of shielding also provide additional noise protection. So I'm not going to go too far into grounding and bonding, but highlighting for you there in the blue box, the TIA 1005A does recognize the grounding and bonding system in three different areas here. The equipotential and mesh grounding system, and it refers to the conductor sizing. It has the diagramming for the star grounding system, which is an isolated ground. And then it also defines an RC, or resistor capacitor device, termination. There is a white paper which will provide you that goes further into these topics. Quick look at some of those shielding components and the range that you can find available for like a control panel application. We're going to talk about patch panels. There are shielded patch panels that are out there. 600 volt rated shielded cabling is becoming very common in the control panel. We're showing you an example there. It is an SF UTP cable. That's in a patch form. It's also available in a cable form in 2 and 4 pair variations. And then you'll have your shielded connectors that are part of that system as well. There is also things like shielded wiring duct that provided an additional layer of protection from noise-producing sources. These are sometimes used in a retrofit situation where you run into a noise problem, you need a way to mitigate it. Something like a shielded wiring duct is an easy one to implement. Okay, so I'm going to move to talking about the actual setup of structured cabling for the testing. So in the environment, plant floor environment, you are likely to see both structured and point-to-point cabling installations. So point-to-point is typically stranded cable, field terminated with plugs, and structured cabling is usually solid horizontal cable terminated with jacks and then using patch cords to connect devices. Structured cabling is very common in the switch-to-switch connections and is what TIA recommends, and it's very appropriate to be using it and is becoming very common on the plant floors. Structured cabling to what is referred to as the horizontal connections or the downlinks in that cabling subsystem 1 is also recommended by TIA 1005A. Extending that structured cabling to this level provides a greater testing ability and the ability to commission and troubleshoot down at that bottom layer where most of those devices reside or in the cabling subsystem 1. In certain cases, such as an on-machine, the field connections are going to be point-to-point cabling as it's the only option available. Recognize that the test methods for point-to-point cabling are going to be different than structured cabling using jacks. Also recognize that with home run point-to-point cabling, really long runs, there's going to be a tendency to make compromises on the cable performance and sometimes the M.I.C.E. factors to control cable costs. So recognize that if you got too much point-to-point cabling, it becomes harder to control the costs on it and provide that performance level as well. So why is structured cabling becoming a best practice on the plant floor? There is a much higher use of managed industrial network switches in the control panel environment, in this access layer 2 and so forth, which makes teaming, patching, and the managed switches together a good practice. So having a good plan for the field install connections that will mate up in the panel makes sense. And in this regard, a patch panel in the cabinet is very much like a terminal strip or an interface module that might be installed electrically for the rest of the control panel. So this is the equivalent of the terminal strip for your industrial network. In the diagram, you can see that structured cabling has a permanent link at the top. That's that jack-to-jack connection with the horizontal cable, and that's typically what's on the end user's plant site. That's what's installed. You also will have the channel, which includes the patch cords that are connected into the permanent link. So following this methodology simplifies the site work as all field connections will land in the patch panels, and then there is a matter of patching those devices to the managed switch. I want to make a quick reference here. So you may be asking yourself, where am I going to find references to these types of standards in my everyday work? You are going to see more and more of these types of references in your industrial control vendors literature. And in all of that literature, you will at least find the component level of cabling and connectivity addressed. The one that I'm showing you here is a Rockwell Automation, Cisco, and Panduit document that is called Deploying a Resilient Converged Plant-Wide Ethernet Architecture. It is a guide all around the physical network deployment. It's an excellent starting point that has both the overall controls network design considerations as well as the appropriate elements from TIA. So if you're looking for a starting point, this is a great place to start. As we get ready to turn the presentation over to Jim, wanted to show you real quickly here. This is an example of what structured cabling looks like in the cell area zone in that probably that level 2 of the network or cabling subsystem 2. In the picture here, you will see those black devices on the left-hand side of the cabinet. That is your fiber connection, your uplink to the next switch level. And then you'll also see the green as well. Those are your horizontal links going out to control panels and devices that are downstream from this cabinet. As Jim talks about the testing procedure and test points, the test points in the fiber are where it's pointing there to the black box, and the test points for the downlinks are there on the right. Also recognizing here as well that in the TIA model, when we're doing the testing at these different levels, wherever we can define a channel. So we would have testing at cabling subsystem 1, cabling subsystem 2, and cabling subsystem 3. The TIA standard defines the method for testing as well within the common standard. Okay, so in summary in the section, please take the information. We're going to provide you this network presentation. Use it to review your internal standards for the network physical layer. We also mentioned a couple of documents in the presentation. We'll provide you links to those as well. So those will be available to you after the presentation. And with this, I am going to turn things over to Jim Davis from Fluke Networks, who's going to talk about the testing methods.
All right, thank you very much for that introduction. Good morning, everyone. Good afternoon. Welcome. My name is Jim Davis. I work with Fluke Networks, and today we're going to talk about how we test this great industrial cabling because we want to make sure it works. A simple objective, but one that'll be important. Now, I'm anticipating that a lot of you are new to cabling, and so we're going to be covering a little bit of the basics. What is it that makes cable support high-speed internet? What's the difference between running 19 kilobits of field bus service over a cabling versus 10 gigabits of Ethernet service? We're going to touch on those M.I.C.E environments and some of the testing that we can do to assure that the cable will have good immunity to the noise, and we might even touch on what some of our test equipment is. Real quickly, I work for Fluke Networks. We make test equipment. We don't make cable, we don't make connectors, we don't do installations. The people who install the cabling and the users who are responsible for keeping the network up and running are the ones who are going to be using our equipment. There's some debate whether cabling is responsible for half or 80% of the problems in industrial networks, and whether it's 80% or 50% certainly gets blamed a lot of the time. I think that's the cabling. So a lot of the time you're going to find yourself having to prove that it's not the cabling, and get the Fluke, put the Fluke on it is a good way to find out if it is the cabling. If it is, we'll tell you where, and if it's not, hand the ball back to the applications group. So we take a look at some of the tools that people are using today if they don't have a good cable analyzer. A lot of times people are going to be using some form of software. Panduit makes an interesting one, Introvision, that can help you to discover the devices that are on the network, maybe factory view, maybe a PRTG or MRTG. And I want to give a quick plug here for using the active equipment on your network to look for cabling problems. Of course, I want to discover the cabling problems before my network has been installed. But if you're using managed switches, you can drill into the SNMP agent, the management agent in the switch, and look for errors that could be caused by the physical layer. These cyclical redundancy check or frame checksum errors are a common sign that you have some problem in your cabling. A lot of people we talk to say, oh, we'll just get the packet analyzer, we'll get the sniffer, we'll get the Wireshark, and we'll do some packet capture. That's a very powerful tool. It's great for looking at things like protocol and timing of protocol. It is not a great thing for finding the distance to where a cable is open or making sure your cable has good next properties. And then we also find people using these little LED continuity testers. Better than nothing, but there's some tools that can help you out a little bit more than that. And pardon this commercial plug, but there's an important message, an important consideration that I want to throw out here. And that is the difference between tools that we can use to, in the telecommunications world, we talk about certifying cabling. Often I hear in the industrial environment, people talk about verifying the cabling. So either a DSX 8000 or a DSX 5000 is a tool that can measure against the standards that the Ethernet application is looking for. We're not just going to look for continuity, but also noise on the cable. Now, simpler tools, sometimes called qualification tools, don't run a complete enough test. They can tell you if the cable goes from point A to point B, but they may not tell you the distance to where the cable is open or if there's something on the far end of it. Now, these tools can be very helpful for the day-to-day management. Is there a switch on the far end of this cable? What is the distance to where this cable is open? And let me tone it out to find the far end of it. Mike mentioned, and I just want to touch again on the importance of standards. People may have disagreements with the standards. They may say that distance isn't long enough. I don't like this part. I don't like that part. Tongue in cheek, I'll say, please join the standards committee. And seriously, they would like to hear your voice. But following the standards is the experience of the industry. That is our best effort at knowledge to tell you this is how you're going to get your network to work. If you are following the standards, the network is just going to run. And if it's not running, you can take a look at the active equipment. We'll see the TI 568 standard, and I like this word that Mike had, the ISO 11801, they are fairly well harmonized. They talk about the same thing. Now within the 568 standard, Mike mentioned this, let me just mention it again. The TI 1005 standard is for industrial environments. While I'm up on my soapbox, why is it that we test the cabling? I'm using great jacks, great cable. I've got an installer who's got a piece of paper who says he went to one of your presentations, Jim. Isn't that enough? No, we want to make sure that when the cabling was installed, they didn't pull it too hard to get it through the conduit. They didn't lash it down with a cable tie too tight and crimp or bend the cable. Experience shows that certified networks run faster. They'll have fewer errors. Cabling's going to be in the wall a long time. Nothing is more frustrating than installing a new piece of machinery. Perhaps you bring your line down to put a new packaging line on the end, and you go to plug it in and it doesn't run. If that's a cabling issue, that can be very frustrating. Speaking of which, something to look for before you pay the people. Did they install the cabling properly? Give me the test results. And I always have to mention, be careful of the people who offer to save money on the installation by not certifying. Oh, my cable tester, it's on the other side of town. I'll give you a discount if we don't have to certify this cabling. Or my personal favorite, this cable is so good, it doesn't need to be tested. If it was so good, show us. So what is it that we're going to test? Of course, continuity, but that's not enough to make sure we're going to support gigabit. We're going to measure how much signal there is, and then we're going to compare that to some different noise parameters and come up with a signal to noise ratio. It'll tell us if we're going to be able to run. Of course, first, we need continuity. And any cable tester is going to give you a well laid out map of all the conductors going from one side to another. Nice green check mark there, a pass to tell us things are good. And this can be from jack to jack or plug to plug. Also, we're going to see continuity with the M12 connectors. Here's a picture. They're a round connector. We find those more often in industrial environments because it's more heavy duty. It's not going to shake loose. Those at M, the I, the C, the mechanical, the ingress, the climatic control. Having a connector that you can screw down is going to make sure that it's not going to come loose. It's less susceptible to dirt or water or moisture interfering with it. There are two flavors of that. We've been using the D code, which has two pairs to run 10 and 100 megabit Ethernet for years and years. More recently, they've come out with the X for Roman numeral 10, 4-pair version of the M12 connector, so we can use category 6A cable and run 10 gigabits communication. Now, the most common problems that we find, and this is important, if there's not continuity on the connector, on the conductor rather, it can't tell us if it's working. Some simple problems, a flipped pair. Now, I've been told that a flipped pair could be wrong on either side, but a secret for you that are out there, this will help. If it's me and there's somebody else working on the far end, it's definitely flipped on the far end, not my end. You can tell them the flute guy told you that. I'm kidding, of course. Not really. Here's a fun one. This little black line says that there's a short. Maybe the wire from your wire shield poked through the insulation, or somebody used a staple gun to attach the cable to the wall, and that staple went through the cable, created a short. That's no fun. There's two different wiring standards, the A code and the B code. I don't care whether you use A or B, but use the same on both ends or you're going to get a flipped pair. Now, one of the more insidious ones is the split pair. And I hate to beat up on those little continuity testers because you're using a tester and using a tester is good. But notice here that 5 goes to 5 and 7 goes to 7. Sometimes it's not always obvious. The striped conductor of a pair isn't always so well striped, and if you mix them up, it's no longer a pair. You have continuity, but terrible crosstalk. So after that, what we're going to look at is the signal strength, and actually we're going to measure how much loss there is in the signal. We're going to inject a given signal into the cable, and we'll measure on the far end the attenuated or reduced signal, the reduced amplitude. We get a graph like this that shows the strength of the signal versus the frequency that we're operating at. This red line here represents the limit line from the standards. A lot of times I try and use a comparison of the cabling standards to the standards for a road, how wide the lanes should be. This red line to me represents the height of the overpass. I want to make sure that all my overpasses have the right height. Now, insertion loss increases with length. So down here, the measured values, this is a 25, 30 meter, about 100-foot long cable. And if we have one that's reaching that maximum length, those 300 feet, those 90 meters, you'll see that it's getting real close to the limit line there. So in addition to increasing with length, we also increase with frequency. You'll notice it's going up and to the right. Our horizontal scale is the frequency in megahertz. At higher frequencies, we're going to have more signal loss. And something that kicks in the industrial environments, signal loss also increases with temperature. So you need to be careful to understand what the temperature is going to be in the environment that you're operating in while you're operating there. You may not be able to go 100 meters. That 100 meters is contemplated on a room temperature cabling, 68 degrees Fahrenheit. And as you get to higher temperatures, you'll see that we need to derate or reduce the length of the cabling to compensate for the additional insertion loss that's going to be introduced there. There's a joke in here about our ceramic oven. We tested the cabling. It was fine. We turned on the oven. Seemed to be a cabling problem. We had to turn off the oven to get close to it. We tested the cabling again and it was still fine. No. Make sure you know the temperature that the cable is going to have. All right, so there's the strength of the signal, and against the strength of the signal, we're going to look at noise factors that we have. One of the noise factors that we have is something called return loss. Return loss is an echo that comes back to us. So we'll transmit a signal down the cable, and we'll listen on the same end that we transmitted for an echo that comes back to us. You see that return loss again is measured the strength of the reflected signal in decibels. It's a ratio of what was transmitted to what is received. So higher numbers in decibel represent less signal reflected back. And again, the red line is the limit, the height of the overpass, if you will, and the frequency. So damaged cable. If I can clearly see on the test results where the cable went into the modular furniture or where it was lashed down to the legs of the machine, that can show up. We want to maintain the separation of the cables. We want to make sure that we are not getting the physical position of the conductors. We want to maintain the physical position of the two conductors, because if we separate those two conductors, that causes an impedance variation. That impedance variation causes the reflection. And our fun one for our industrial environment here is getting water in the cable. Yeah, this is actually what return loss is going to look like if you have water in the cable. Now, this doesn't necessarily mean that it's a bad cable. It's just not the right cable for this application. There's our M.I.C.E, and I believe it is the C in M.I.C.E for climactic, or perhaps the I for ingress, where if you're getting water in there, you need to use a more robust cable, something that's got a jacket that's more waterproof. All right, another noise parameter is near-end crosstalk. This is interference that goes from one cable to the adjacent cable. In the olden days, when we had phones in our houses, you could pick up a phone and sometimes you'd hear your neighbor talking. Now, same thing happens in the cable, where we'll have some signal that is induced from one of the pairs to an adjacent pair. So we'll inject a signal on one pair, and if we listen on the adjacent pair on the same side, we'll get near-end crosstalk. If we listen to that adjacent pair on the far side, we get far-end crosstalk. Now, this next part of it actually comes from the connectors and the design of the connectors. I hate to beat up on the RJ45. It's a great connector. I love when I travel. Everywhere I go, it's always an RJ45 connector. I have 5 or 6 different plug adapters so I can get electricity from my laptop, but always the same RJ45. Again, following the standards makes things easier. But having that 4-5 conductor inside the 3-6 does introduce some noise to it. Damaged cable can increase next. Not maintaining the twist opens up the possibility of getting that. And another important point I want to bring up, hopefully this is showing up on the bottom of your screen, is having the wrong test limit. Your test limit, your requirement is category 6, but the guy at the store told me this is really good category 5E cable. It probably passes cat 6. It's so good you don't even need to test it. I want to bring this up because sometimes there can be some confusion on the M.I.C.E ratings. If you have a product that is rated for a M.I.C.E 1 zone, but you test it against a M.I.C.E 3 zone, it may not pass. If you test your category 5E, your really good category 5E cable against category 6 or 6A limits, it may not pass. All right, so we're going to put the two of these together and we're going to come up with our signal to noise ratio. I want to look at the attenuation to crosstalk ratio here. We're going to start with category 5E, which we test to 100 megahertz. Here's the limit line here. Now I'm going to try and put my mouse right up at the top here of the limit line. Category 5E can run 10 and 100 megabits Ethernet, runs gigabit Ethernet just fine. It'll even run something called N-base-T, which is 2.5 and 5 gigabits Ethernet. Yes, if you followed the requirements of the standard 20 years ago, today you can get quite a bit more speed out of your cable. Now, some people say I'd like a little bit of margin. Now, when I jump to category 6 here, you'll see that the limit line not only went out to 250 megahertz, but it went up a little bit. There's that little bit of extra margin. Cat 6, nice margin over 5E, can support 10 gig out to about 50 meters. And category 6A is going to run to 500 megahertz, we see out here, and that's going to be adequate to support 10 gigabits all the way to 100 meters. I'll save my conversation on category 8 for another day. Moving right along, if there's nothing else you remember from our presentation today, these next 2 slides are real important. This is the test result. This is the proof, the warranty, if you will, to you that the cabling was properly installed. Real nice, colorful graphs, numbers, plots, 2 fields to read on here. One, did it pass the test? Yes. This one did. And the other field that's real important to read is what limit did it pass? And over here, we'll see that this was actually tested against Category 6 limits. So if you were paying for Category 6A cabling, this hasn't passed. You might want to ask about that. That's great for your office environment, but hey, we're in an industrial environment. We'll jump into our trusty M.I.C.E chart. And again, as we go from the 1 to the 2 to the 3, we're moving to increasing environmental severity. There's going to be more electromagnetic interference. What we worry about with that electromagnetic interference are going to be these CRC and FCS errors. What is a cyclical redundancy check or frame checksum errors? Well, technically it's caused by the checksum generated by the transmitting device, not matching the one generated by the receiving device. What happens is we're transmitting ons and offs, and if our off gets some interference on the wire while it's being transmitted and turns into an on, that frame is corrupted. The frame cannot be read, and it'll be thrown out at the physical layer error. It's okay. Ethernet is robust. It will keep going. But in your industrial environment, you may run into a problem, especially if you've got a machine that has a high requested packet interval. Could be that everything is running fine in the factory, but before you move that ladle of molten steel, you want to make sure no one's standing underneath it. So you call your security system. Security system, are you there? This happens automatically, of course. Yes, I'm here. Security system, are you there? And the frame coming back from the security system is corrupted and you don't get it. And you ask again, 2 or 3 times, you don't get an answer from the security system. Shut it all down. Nothing's wrong, but I'm not hearing that that's happening. Let's drill in a little bit of painful detail here about what the cyclical redundancy check error is. Here we talked about Wireshark or sniffer packet capture. Here is an Ethernet packet. Now I'm going to simplify this quite a bit. We're going to say that at the start of the frame, we have a destination address where it's going to. It's followed by the source address where it came from. Protocol, are we going to speak English, Spanish, HTTP, voice over IP? The actual data, the cargo, the information, yes, I'm still attached. And at the end of all this, we have a little frame checksum or cyclical redundancy check. And that's just a little algorithm to make sure that all the bits and bytes in the frame are in the right sequence. So here we go. We've got our cable, our switch, and our PLC, and we're going to transmit a real simple message, on, off, on, off. So we'll send on, off down the cable, and we get on, off, on, off. Great. Our CRC value is true. This frame is in good shape. We can accept it. Now we're going to transmit that one more time, and I'm going to push the limits of GoToWebinar for animation on the Ethernet. The interweb, if you will. So we're going to transmit 1010, but this time somebody's going to turn on a 100 horsepower motor right next to the cabling as it's being transmitted, and we'll get some electromagnetic interference. And what was on, off, arrives as on, off. There's our CRC error. We need to throw that frame out. So what are we going to do about this electromagnetic interference? Well, a couple things we can look at. One option is we can use shielded cable. If you're going to use shielded cable, could be individual and overall, braided, foil shield, check it to make sure that that shield follows the path of the cabling. The standard actually says needs to follow the path of the cabling. We have an interesting trick with ours where we're going to check to make sure that the shield follows the path. Now, if we just did a simple continuity check, you can see that there's continuity between these two shielded connectors. But in the cable tester, it says, wait a minute, the intern who you had terminating this cable tore off the shield and didn't terminate it, so the shield is open on one end. This may also be interesting if your standard is to make sure that the shield is open at one end, given your concerns about ground loops. All right, the other way that we can avoid noise on the cable is having an electrically balanced pair good symmetry between each leg of the pair. If each leg of the pair treats the interference in the same way, we can cancel out the noise. This is why unshielded cabling works. The signal I want to transmit is +2 volts. I'm going to send +1 volt on one leg of the pair, and 180 degrees out of phase, I'm going to send -1 volt on the other leg of the pair. If the cable is well balanced, even though it's received some interference, we're going to maintain that 2-volt differential. Now, if our cable is not well balanced, that common mode noise that is induced onto the cable may not be received equally by each leg of the pair, and we fail to maintain our 2-volt differential, which causes our problem. There's a view of it on one of our trusty oscilloscopes. So how do I make sure that my cabling is well balanced? Well, there's a parameter called transverse conversion loss, and the definition, we're going to send a differential mode signal down the cable and listen for common mode signal coming back. Most of the noise that's induced on the cable is common mode. If it gets, and we can ignore that, but if it converts to differential mode, that's where it may cause the corruption. So the important thing to remember about TCL is this is going to make sure that our cabling has immunity to this interference. Now, in the basic standards, and this comes from a standards document we post on our webpage that shows us the different limits by frequency for signal strength and noise according to different standards. But in the basic standard, you'll see that there is not a requirement to test transverse conversion loss. However, if you select a more complete test, these plus all tests, we're going to add in some additional parameters with limits for them. So selecting the plus all test will include the TCL values. Now the TCL values come from the standard. The manufacturers are required to test this in the factory to show compliance. It's just not mandatory for a field test. And we're also going to test TCL's friend ELTCTL, which is TCL measured on the far end, a little bit like far end crosstalk. So this is the big difference between an E1, an E2, and an E3 environment when we talk about, say, category 6 cables. These limits are going to 250 megahertz. So here are category 6 limits, the strength of the TCL in decibels versus the frequency. And the return loss, the insertion loss, is all the same across M.I.C.E. 1, M.I.C.E. 2, and M.I.C.E. 3 environments, but it's the TCL that is going to be stricter. Now, as we move up from E1 values to E2 values, you see that the limit line is tighter, is stricter, and this represents better noise immunity. And again, in E3, we're going to step up the TCL requirements one more time because they are that much stricter, tighter, harder to pass. So again, if you're going to test to E3 limits, you may have an E3 environment and say I want to test to an E3 environment, but you need to use E3 components to make sure that they'll pass that. So Jim, this is kind of helpful. What should I say in my bid document? What should I ask for? I'm not the right person to ask. I don't care if you're doing copper, fiber, shielded, unshielded, single mode, multi-mode. I'll tell you how to test it. It's your consultants, your architects, the engineers who are familiar with your environment. They're familiar with the components that they've specified to be installed. They know what applications you're going to be using, and they know what the environment is. They can put all that information together to decide what is the correct test limit. Working from there. Now, as much as I'd like to have a 9-page specification, don't always have that much space. If I only had one cell on an Excel spreadsheet, which has to be half the specifications I read, I would say something to the effect of the links shall be tested to the NCTIA 568.2 for copper. D revision is the current revision. Limits for the category, is it 5E, 6, or 6A? 5E is kind of the lowest performance, and E1 is going to include those TCL values for an E1 environment. You might start there and work up as you have higher performing equipment. Quick commercial blurb. We make a tester. We've got an industrial version that has M12, D and X code adapters with it. Make sure you ask for test results. This will show you that your cabling has been properly installed. Summarizing, follow the standards to make sure your cabling is going to work. Check for that limit on your test report. Did they test it to the limit you asked for? TCL measurement will confirm that your system is well balanced, has the noise immunity, and using the right tools will reduce your startup time, and using the right cabling will also make sure it works in the first try. Folks, I'm running a little bit long, but I think we may even have a few minutes for questions. And a quick thank you to CSIA Panduit for inviting me along for this conversation today. Jane, did we get any questions out? Thank you.
You know, we did get some questions in. We'll take a few moments now, so if you have any last-minute questions, please enter them in the GoToWebinar app. The first question here is, I know this is a copper-based seminar, but would not some version of industrial PON eliminate most of the issues related to the placement of copper-based systems in the industrial or manufacturing setting?
Yep. So I can talk to that, and Jim, if you want to, you can talk to it as well. So on that slide, we were showing the shielded cabling. Of course, when you get to that E3 level, fiber optic devices and cabling could obviously have application to mitigate that noise level, and that is done in certain applications using the fiber connection. So that's a great point. I think the PON might actually be the plastic optical networks. So the availability of product and devices at this level is not as strong. So you're going to have a lot of copper need, a lot of copper-based devices at this level of network where you need to address the noise factors. So Jim, if you want to answer, go ahead.
Yeah, I'd throw something out. I wasn't sure if that was plastic or perhaps a passive optical network.
Okay, yeah, passive.
And either way, Panduit makes copper and fiber. We test copper and fiber, and certainly fiber has great noise immunity. It won't work in all situations because plastic and glass are terrible conductors. So if you need power, that's not going to be the solution. But absolutely, there are environments. Had a customer who was doing an installation up on the roof of a TV station. There was so much interference there, they had to wear meters on them to make sure they weren't getting overdosed with the radiation. Sorry, copper is not going to work great there. So absolutely, fiber will have a time and a place in those networks.
Looks like, guys, we have time for maybe one more question here. Mike, it looks like this one may be directed at you. It says, what is the difference between M12, X code, and D code? Okay.
So Jim actually addressed that a little bit in the presentation where he was showing you the newer device with the 4 pairs, which is the X code, and then the D code, which actually uses 2 pairs. So you're going to find the D code has been out there a little bit longer. Those are going to be connections made to like your smart blocks or smart modules are made with a D code type connection. And then what you're going to find with the X code are more of your processor-based connections, your wireless access points, RFID systems. Some of the switches are based in this format as well. And so it's kind of an emerging technology is the X code. So it uses the 4-pair connection. Performance levels, D code is usually 10/100 and a category 5E. And the X code is usually Cat 6A and a gigabit performance.
Jim, did you have anything you wanted to add to that? Are we good?
Thanks for showing that, Jim.
Thank you. And we actually are just at 11 o'clock, so we are going to go ahead and conclude the webinar. Thank you so much for your time today, and you have a great day.